All right. Evening, everyone. Tonight we're going to get back into some friction, kinetic friction. I've decided to put just a little bit on the homework, so I'm going to do maybe just one more diagram. I'm not going to do any big examples like last time. So I kind of have a demo up here. But first, let's draw a picture of kinetic friction. Which type of friction is this? Is this the staying still one or the moving one? It's the moving one. Why? Because it says kinetic. It means things that move. All right. So whenever something is moving, the sort of molecules and atoms, the sort of structure of how the object is made sort of rubs across the structure of what it's sitting on. So this is going to be sort of a wood surface on the bottom. And you probably already know wood isn't perfectly smooth. There's sort of little holes and bumps, little jagged things in there. And we have a wood surface table. So let me just draw a little diagram. So repeating what I kind of did last time. So zooming in on where these two things are sort of contacting one another, that little cross section right here. We have these sort of jagged peaks from this box up here. And we have jagged peaks, valleys from the table. And we're going to be pushing the box on the table. So you can imagine those sort of hills and valleys, they're just like grinding on top of the other one. They're sort of bouncing, riding up on top of them. As we sort of push or pull things together. And all things that touch one another have some type of friction. When it's standing still, it's static friction. When it's moving, it's kinetic friction. Typically, the kinetic friction is less. And that's sort of what I was talking about last time with, static friction being a little bit more than kinetic, like trying to push, imagine pushing your fridge. It's hard to get going at first. Same thing with a box or, anything up here. It's hard to start moving because static friction is different than kinetic. But as soon as it starts moving, it becomes a lot easier to push. How can I express this in an equation? Last time I've written something like this. Nope. It was K for kinetic friction. And it's multiplied just by some number. That's the coefficient of whichever type of friction, so static or kinetic friction. This one would be kinetic. Multiplied by the normal force, F sub n. That's what I call it. So if I'm going to be pushing, or in this case pulling, this box, a certain amount of force in one direction, we have to always remember friction opposes movement. I'll sort of write that. I think I wrote that last time. Let's see. I'll write it again this time. Friction opposes the direction of motion. All right. And unless it's some sort of very specific or special material that sort of has peaks and valleys angled some way, I don't quite know of any materials off the top of my head. But if I push something this way, it's the same amount of friction as if I push it this way. Friction is always trying to keep it to stay still, wherever it is. So if I'm going to, yeah.
Does it work the same with spheres?
Spheres?
Yeah, because they're not as hard to do.
So if I'm pushing a sphere so that it will drag, then yes. There's also another type of friction called rolling friction. I'm not going to cover in this class, but it's something that, if you get more into rotation, things that are rolling, like tires, they don't slide on the ground, they have to roll on the ground. So they need a specific amount of friction. That's just called rolling friction. But in the case of your question, like if it's a sphere, that's just like dragging. Then yes, it has either static or kinetic based on what it's doing. Okay, so let's say I have a object or whatever. I want to drag it with a certain amount of force. The right one. And I want to, let's say for the problem that says find the coefficient of kinetic friction. So all I need to do is find, the normal force, and the force of friction. Well, I don't believe I drew a free body diagram of friction. That's kind of what I'm doing right now. So for you guys, it's going to be going to the left. So let's make it so there's a box. I'm going to pull to your guys' left. First, for this free body diagram, just always remember you don't have to draw the picture. I drew a box and a table. You could just draw a dot. That's fine. But I have to know what type of forces are acting on that box. So it's sitting on a table. Gravity's trying to pull it down, and the table is holding it up. So those are the vertical forces. So let's list those out in the picture. And I might pull or apply a specific constant force to this box in one direction. So you guys see the wood side is down right here. Okay. I think it goes about 4. Once I kind of get it going. The constant force is about 4. A little bigger? Smaller? Okay. But it's a constant force in one direction. To the left. I'm just going to label this as pull. It's me pulling it to the left. You can label them whatever you want. Whatever makes sense to you. Force of friction always opposes movement or motion. So the force of friction in this case is going to be to the right. And if I've drawn these forces to scale, remember you can actually get a ruler, draw them to scale. You can draw the force of friction to scale. It would be a rather small. It's going to be a very small force opposing it that way. So it's opposing the motion. And I guess I've written it as lowercase f sub k. Yeah?
Because of the way you're pulling it, does that mean there's an angle there?
I guess in the my specific, yeah. If I should have been more flat. I got to be up a bit. Yeah. For the perfect example, this scale isn't that big, and I can pull it directly horizontally. Right. Okay, so in this instance, depending on what they give for the problem, in order for me to find the coefficient of static friction, I want to solve and find this guy right here. So I need to know the normal force. I need to, know the mass of the object, and need to find the normal force, the thing that holds it up. I also need to know the force of kinetic friction, and that is going to be this portion, and that's a part of me summing the horizontal forces, right? So remember from last time, I did like 20 examples. Some of them I summed just one, or horizontal or vertical. Some I did both. In this instance, to find the kinetic friction, that would be part of the horizontal components, the opposing in that way. All right, just for fun, we're going to see, so we have wood. Let's do carpet. So it's carpet on like a smooth wooden table. I think it'll be, I already looked at it. What it'll be. Do you guys think it'll be more or less? How about that?
More.
So it'll take more force for me to pull it at kind of that same rate. Yeah, let's see. Was it more?
More.
A little bit more. Just a little bit. These scales aren't perfect either, so they're just for demonstrations. Now, we have rubber on wood. It's going to be more or less.
More.
So it's going to take more force to pull it the same amount, that same speed. And why is it more force? It sort of boils down to there being more friction, or there's a bigger, coefficient of friction of rubber. Was it about 10 or something?
6.
6? Ah. Okay. Anyway, so that's friction. Yeah.
So I'm just a little bit confused because, well, first of all, is the friction force vector, is it smaller than the friction or the force pull?
Yes.
So doesn't that oppose Newton's third law because that's every action has to have an equal and opposite reaction? So it's not equal to the force pull, right?
So for that instance, you gotta imagine for my free body diagram, I'm only looking at this sort of enclosed space, this bubble. The Newton's third law would apply to me pulling with that same force pull. So the box is pulling me that way with the amount of force, or F pull. Does that kind of make sense?
Yeah.
So whenever we do a free body diagram, we're just closing in on that specific object. I'm gonna kind of go over that in a bit, but right, it does kind of like going back to Newton's third law. Seems like it doesn't make sense, but for all of these free body diagrams, we're just looking at that, whatever. You don't see in the diagram, you don't see my hand pulling it because the force pull is, pulling me that way. If that kind of gets that across. Okay. All right. All right. Tension. It's another type of force. that is exerted through some sort of string, rope, cable, wire, I don't know, elastic. It's a force that travels through an object, parallel to the direction that the thing is going. And it's equal in both directions. So if I have, say, a person over here, playing tug of war with something, a rope, the force of tension is equal in both ways. Say there, it's a stalemate. The tension pointing that way is the same as the tension pointing the other way. It travels through the cable or rope or anything in the same direction. So that's with stick figures. Let's do like, let's see, same as like a hanging mass. You hang a mass. I have this up, might as well use it. I have a hanging mass. There's tension both going up and down in that string. Okay, so how do I actually draw tension on a free body diagram? Free body diagrams that shows where the forces are pointing. And tension goes in the direction of the rope or string. So in this instance right here, free body diagram will look like this. Very, almost identical to all other cases. Gravity wants to accelerate that mass downward. So that's a force of gravity downward. But now it's tension that is holding the thing upward. It's pointing up. And commonly you could just label it as T. And so, right, again, Newton's third law instance, tension pointing up. But from this perspective up here, there's tension pulling down. So just imagine you have like a magnifier glass over whichever area you're looking at. Okay. Right, and so we can have tension in like a variety of different problems. Now we don't need, for a situation to be like, there's a box on a table, there's a car on a table, there's a sled on the snow, like surface to surface. Now we can actually find forces that travel in like a variety of different ways because we're connecting two things via like a string or a cable. So vertical, something like this. I'm just going to do a little picture of each. Something like that. And for all of these examples I'm doing, before I like blaze through this, it's just another way of summing forces. So whatever the type of problem is, you would then sum the vertical forces, and then you'd sum the horizontal forces. In this case, the vertical, there's only vertical. There's like, tension upwards, downward. Vertical accelerating, that's kind of like the example I gave last time of a person in an elevator moving upwards, accelerating upwards or accelerating downwards. Except now, it's this thing. You know, imagine this is like a crane. It's pulling it up at a steady rate. We're lowering it down. What's the acceleration? You know, there's a variety of different problems. In this case, it's easy. It's still vertical. Symmetric angles. Here we go. Let me draw it first. So what if we have something that looks kind of like this? Nope. So here's the ceiling, or you know, just like a immovable surface, and we have something like this. And the symmetric angles are these two angles that are theta. So you could picture this as like two ropes going in two different directions. One long rope. Let me actually set up the one long rope. Picture like this could be how. I move it too far. Maybe. So this is very useful in like figuring out tensile strength of rope or chains. Is this chain safe to lift this car? That's a mistake you don't want to make. Very expensive mistake. So let's look at something like this. Okay, there we go. Somewhat in the middle. Something like that. How much tension is in the rope now? It's symmetric for you guys. Well, we can actually kind of get through this experiment together. So I picked an easy amount. This is already measured in newtons. This is 10 newtons. And if here we go, this is why. Before I do this. Okay, just to show you guys, this is 10 newtons. Straight down. Roughly, again, these are sort of stage scales. So 10 newtons force of gravity pulling down, 10 newtons tension directly upward. This is a straight up and down vertical problem. Now, something symmetric, something that looks like that. I messed it up. This over here. Look like this. Now, what do you guys think? What's the tension going to be in the string? This is if this is symmetric. I'm going to try to make it middle. Oh yeah, it is. Who thinks it's 5? Who thinks it's just not 5? Any other number but 5? Okay, let's see. So I'm going to put this right in the middle. They are roughly the same. Okay, they kind of make sense. Certain amount that way, and its exact equal is pulling that way. All right. Also, you see how this problem right here It's symmetric two ways. It's going to use probably some trigonometry to sum the forces. Left, right, up, down. Going to have some forces that way. The next really fun one is non-equal angles. So in engineering, construction, all of that, you don't always get perfect symmetric problems or, very easy solutions. Sometimes things are offset. So we're going to have to deal with that by knowing how to handle these non-equal angles. So something like this. Just like that. Okay. That one right there I'll call phi, and this one over here I'll call theta. So we'll have to figure out the tension in these two. Again, by splitting them up, using our sines and cosines. In this sort of example I have up here, I have one, I guess this is kind of off-center. This isn't too off-center, this is just a little bit. Still kind of. Oops. This one's less. Okay, next. What if we lean over a bit more? So now you guys can kind of see that this portion of the string right here has to do a lot more work, a lot more sort of effort holding the mass up. This one, not so much. But it isn't sort of a perfect split, with that symmetric case. That's what I'm trying to get at here. And if I go all the way over, that's just basically hanging the whole thing off of this scale on this side. This one's doing basically nothing over here. All right. I don't want to go over these examples too much because basically the examples I would do are kind of in your homework already. All of these things that we've learned, yesterday, last time, examples with summing the forces, tension, friction. They're just sort of summing the horizontal forces, summing the vertical forces, and that's basically it. Solving for what they ask for. Okay, what if a problem gets to be a bit more complex? This is one mass that is staying still. Right here. I guess I'll leave it up for right now. That's one mass, staying still. I don't have to worry about it moving, accelerating up and down. Maybe I might have a problem or two like that, but I'm just focused on that thing. That's what's going to bring a track in a car. Never mind. But what if I instead have a couple things to take care of or to watch? Let's see. How do we manage when we have more than one object? Let's see. Next week, I believe you guys are doing like a Newton's second law lab, and you're going to have a track. You're going to have a track with a mass on one side that will drop, and it's going to pull a car that way. And you got to figure out, like acceleration of the car and some forces that are involved. So that's going to be a car attached to a other object that is falling. Let me draw that, because that's just sort of the example I'll use. Do that. There's like a pulley. Right, as the mass over here, the mass off of the edge falls, it's going to accelerate downward. That means it's going to pull the car that way. It's going to accelerate the car that way. These two things are connected together. And they're connected by a string, or whatever. So that's a tension. That's a tension force. Okay? How do we sort of deal with this when we have more than one object? That's what we're going over with looking at the thing when we're drawing the free body diagram. Looking at the thing in its own special bubble. So let's draw the free body diagram of each of these two masses. So for mass 1, so I don't care what it looks like, I'm just going to make it a dot. I'm just going to sum the forces acting on mass 1. So in this instance, it would be a car or a block sitting on a table. Same as always. Force of gravity pointing downward. The table is holding it up. We've got that normal force pointing upward. And in my picture, it's going to be pulled to the right. All right, so I'm just going to label a force to the right as the tension, or T, because it's being pulled by a rope. So how am I able to sort of see this again? I'll draw it on here. You just sort of pick out what we want to look at. Draw a nice little bubble around it. Just so we want the forces just around that thing. We don't care what the other mass is doing right now. Do the same thing for that second mass. Draw a bubble around it. That's all we want to focus on for this next free body diagram. So for mass 2, in this case, it's a mass. It's going to be dropping. It's accelerating downward. So there's that downward force. And there's nothing pulling it left or right. The only other force is tension, holding it up a bit. Like that. Yeah?
Is there friction for the first one?
In many problems, they'll say that's where you need to look to see if it says frictionless or not. But you're right. If for the first one in real life, real life, there would be a small amount of friction in the other way. So that would be like the real life example. Friction is always opposing the movement. Yeah?
For the second mass, would there be any air friction?
Technically, yes. But this is where we get to the, teaching the entire thing right to you guys right out of the gate makes it very complicated, right? Like adding that little small friction makes the problem more complicated, right? Instead of 0 is a nice number to deal with, I now have to deal with friction. I then would have to deal with air friction going up and down. So all of these times in all of our problems, it'll just say like a frictionless track ignore air friction, this and that. We would just take the sort of perfect example and not include friction. And we do this just so you can kind of understand what's going on before we make it too complicated for you. Okay. All right. So I have a couple of, small, a little bit more complex examples. That same sort of thing I just drew. There are also, I could have chosen a homework problem like that. But this is sort of, dealing with these two individual masses separately and finding out, summing the forces up and down, left, right, figuring out what they're asking for, like acceleration or a force. You can kind of see how these are doable at your rate. This is where we can, sort of lead into how things can get more complicated in the real world. We have a more complicated situation. Something like this. The thing about pulleys is that if you add more pulleys, the amount of force you need is reduced. I didn't want to bring out like 40 examples, but we have one where adding more pulleys means there's less force needed to lift an object. Or this example, the question would be like, how fast is, or what's the acceleration on the middle mass? These are some examples of how things can get ramped up. For instance, I have single pendulum here. Very nice, very fun. Then I have a double pendulum. Just adding one more thing, I know how to go step by step. I can take it nice and easy. But adding a little bit more, like adding friction, can then start to make things more complicated. You try to find the motion of that. If you guys want to see after class, we have a triple pendulum. You just come down and let me know. The cool thing about this double pendulum is I can restart it and it won't do the same thing twice. Okay. And these are sort of like examples outside of the scope of this section. We'll talk about pendulums later when we get into rotation. But this is another example of, this is a coupled pendulum. We have, you can kind of see, if we want to focus on one, we would draw a bubble around one. Okay, there's one, but there's a spring sort of acting on it that way. This one, there's a spring acting on it that way. The cool thing about this one, I'm going to go like this, is that they'll sort of transfer back and forth the amount of energy. I'll just let those go because they're fun. Okay, some neat examples. Lost my pen. I think that is it for this chapter. Does anyone have any questions on like forces or tension or friction? Anything? All right. We're going to move on to the next chapter, which is energy. Okay. First off, what is energy? You might think like, we got it like an energy bill. Some people may say power bill. What's the difference between those two? There is a difference. I wake up, I have energy in the morning. Sometimes I don't have energy at all. After I teach this class, I have zero energy. Let's see. Energy is, let's phrase it like this, a way to see how much work can be done by a system. All right. So, there's different types of energy. There's like, we'll get into like kinetic and potential energy. There's thermal energy. There's chemical energy. The basic definition is a way to see how much work, I'm going to underline work, how much work can be done by a system. When I have a lot of energy, I can do work. Is that what we're meaning here? Let's ask, what is work? So let's first write, I'll write the equation. And this is why I didn't like using W for weight, because we use W for work. Work equals a amount of force over a specific distance. So I'll say it's sort of a cyclic definition, the amount of energy. No, I'll say energy. Energy is a unit of joules. Energy required to force an object over a distance. Okay, so basically, when I do work on a system, I have to sort of input some energy into it. So me forcing this thing upward, I'm adding my own energy to the box. So I'm adding energy as I apply a force and I change its distance. So upwards like this. So I'm adding energy. Or if I constantly move the box one way or the other, I'm applying a force, changing its distance. I am adding my own energy to the box. This is where the case again where we look only at the box. Okay, let's see. In more detail, I'll say that work is force times cosine theta times the absolute value of however it changes. And the units for work, let's go like this. Force times this. So the unit of work is a joule. So 1 joule equals the unit of force is newtons. 1 newton times the unit of distance is meters. SI units. All right. So I sort of got into it a bit. Work can be done on an object. Should have brought out spring. Use that. So work can be done on an object. Let's take, for instance, if we had a spring. And this is where it sits normally. In fact, let me get a spring. Okay. So say we have a spring and it has a natural sort of resting state of this length right here. Okay? And I apply a force to it. And I'm going to try to stretch this spring like this. So I am taking this spring and I'm forcing it that way. So let's see. I'm going to say work can be done on an object. Work done on an object is positive. And since it's positive, this will increase the amount of energy in the system. Okay? And so by applying a force, displacing its distance, over a distance, I'm going to say right here, by applying a force, over a distance, work is done. On the spring. I'm going to underline on the spring. Okay. So, again, try to imagine like this spring that has a certain amount of energy in it already. And when I force it, it now wants to retract, right? So it is at a higher level of energy. It wants to go back to the way it was. So I am applying a force over a distance. I'm doing work on the spring. Therefore, there's more energy in the spring now. Okay. And it's basically just the reverse of this for work done by an object. So I'm just going to get all the pictures up first. Work done by an object is negative. See this? By an object is negative. And so, I could say the exact same thing except the other way for this one. So I'm going to sort of summarize it by saying I now have this outstretched spring that I will let return back to its natural state. And I'll say over here, my hand removes some force over a distance. So work is done by the spring. Okay, so in this case, I am forcing it outward. And so now imagine, as we start to go back this way, only looking at the spring, not looking at my hand. The spring is doing work, pulling it back to its original state. So work is done by the spring as the energy decreases. Yeah, so this is kind of a place to get sort of lost in it. There's work done on an object or by an object. They are two different things. Let's see. I think we have time for, we'll just do like an example, and then we'll see how far we go. Yeah, that'll be good. Okay, so a 3,000 kilogram truck is being lifted by a crane and placed onto a cargo ship. The crane applies an upward force of 31 kilonewtons and lifts it to a height of 2 meters. What is the work done by the crane? Work done on the truck by the crane. Okay, so let's draw this example real quick. The crane is lifting it upwards with a certain amount of tension. I'll just label as T. And this is an object near Earth. It will feel the force due to gravity. There's no left-right forces, so we're only going to be summing the vertical forces in this case. All right, so what is the work done on the truck by the crane? Okay, so the work from the crane, let's say work from the crane, and just going back to what the equation said, it was force times distance. So this is the force that the crane applies. And I'm just going to say it's delta y because it's vertical up and down. All right? And it becomes a very simple problem. We already know distance. We know a force. This becomes just 31 kilonewtons. Got to remember it's kilonewtons. Times 2.0 meters. 2.0 meters. So it should be about 62 kilojoules. So I could transfer it back to regular newtons and then find regular joules. But since it's a 1-to-1-to-1 ratio, I can say a kilonewton times meters will give me kilojoules. So I'm going to say it's 62 kilojoules. Okay, so right, let me change the picture so for people following along with the picture. This is labeled F, crane. That's the force the crane is applying upward. All right, the work done on the truck by gravity. On the truck by gravity. Okay, so the work done by gravity is equal to the force of gravity times however far the truck moves, or it is moved. Let me just do that. There we go. Now we're not given a force of the truck, we're given the mass of the truck. So that means we have to do just a little bit of extra work. That's perfectly fine. Because F sub g, it becomes mass times acceleration. I should make this negative before I get too far, right? This is where we also remember downward forces or downward vectors are negative. Things moving to the left are usually negative. So we have minus, I think it's 59 kilojoules. And then what is the total work done? We just add the amount of work done by all of the forces in each of the directions. In this case, it's only the two, so we add these two amounts of work. I'll say net or total. Grain. Gravity. 62 minus 59. So our net work done is 3 kilojoules. Okay, so that means that 3 kilojoules worth of energy are added into the truck just by the truck being raised up off of the ground. Okay. Yeah.
Is 59 is an approximate value?
Yes. I have to round to 2 decimal points because I only have 1. I should only do 1, but I'm doing it to 2 decimal points. All right, I think, let's see. That's energy. Yeah. I think we can leave it here. If you guys have any questions, or also, before you go, if you haven't picked up your quiz, I have quizzes up here. You can come down, come get them. I will also put out the triple pendulum for people who want to see it. There will be a quiz next Tuesday. All right, awesome. I'll see you guys later.